Hey guys, I'm Professor Jennifer Hill, and this is my YouTube channel, Divide and Conquer Math, which is a YouTube channel and a website designed to help you learn math on your terms. And in this video, this is part of my Study with a Math Professor series, so this is the fourth video in the series on limits. So the purpose of these videos are to help you prepare for a calculus test on limits. And these videos really align with my philosophy of how to study for a test, which is to practice, practice, practice. So if you've never heard my philosophy of how you should study and kind of what works best, I highly recommend that you check out my video about that. So I'll drop a link to that in the description below. And you're also going to want to get a hold of the problem set. So in this video, we are going to go through just all types of limits of mixed levels of difficulty. So just kind of anything goes. They could be pretty easy, they could be pretty hard. So this is kind of a great video if you've been doing the previous three. This could be a really great video just to make sure that you can really handle anything that's being thrown at you. And the problem sets always come with an answer key, and then for each problem, if you just have no idea how to do it and you're looking for more of a lesson type approach, I've got links to other videos that you can watch. So basically between the problem set and this video, you'll get everything you need to study. So if you notice that you get one of the problems wrong, you'll notice that in the description I have time markers for every single problem in this video, so you don't have to search through everything. So you should be ready to go. We're going to start by, I'm going to have a 1 hour timer. You'll see me working on some stuff. That's just kind of there in case you need some extra motivation to help you study. So that's like you can think of that as a 1 hour timer for you to kind of shut off all distractions and just work. And I'm super curious to know what you guys think about this video, or if there's other things that you guys might want to see or suggestions that you guys have. So feel free to drop me a comment below, and otherwise let's get started. Hey guys, I'm going to start the problem set, so if you are not done, hit pause here, or you can start the study video again. So starting with number 1 here, so this problem is simplified as much as it can possibly be. We've got the limit as x approaches 3 of x minus 4 over x plus 2. In this case, this is continuous at 3, so I can really just plug 3 in, no problem. And so I will get negative 1 over 5. For number 2, so I've got the limit as x approaches negative 2 of x cubed plus 2x squared over x cubed plus 8. So in this case, I notice that I can factor the top and the bottom, and I also notice that if I plug in negative 2 into this particular problem, I will get 0 over 0. So just a note, so you get 0 over 0, so that's the indeterminate form. Anytime you get the indeterminate form, that is going to kick off that you need to try something else. And I noticed for this particular problem that I can just factor the top and the bottom. So let's see, out of the top I can factor out x squared, so that leaves me with x plus 2. And then in the bottom, so this is a perfect cube, or this is the sum of cubes, so this will factor as x plus 2 times x squared plus 2x plus 4. And so you'll notice the x plus 2's will cancel out. So now I just need to take the limit as x approaches negative 2 of x squared over x squared plus 2x plus 4. And so here, now I can just actually plug in negative 2. So notice prior to me actually taking the limit, I've kept my limit notation, consistent. Make sure that you're very consistent when you write out your limit notation. If you haven't taken the limit yet, you shouldn't be dropping the limit notation. Okay, so let's see. I'm going to plug in negative 2 like this. So I get 2 over 4 minus 4 plus 4. So this ultimately will equal 2 over 4, which equals 1/2. So for number 3 here, so I've got the limit as x approaches 5 on the right of 1 over x minus 5. So notice if I try to plug 5 in, I'll get 1 over 0, so that's a problem. Also notice that I cannot simplify this anymore. So what that's telling me is that probably this is going to end up going to infinity, so I need to find some way to kind of analyze that. And one of the best ways to do that in this case would be to use a table, so let's set up a table. So here are 3 values that are getting closer and closer to 5 on the right. So if I were to analyze those, here are the values that I would get out of this particular function. So you'll notice the closer that I get to 5, the bigger this number gets. So the closer I get to 5, this is really just going to continue to get bigger and bigger. So this is going to equal positive infinity. That's where this is going to. So if you want to try more limits like this, I highly recommend checking out examples on infinite limits. So for number 4 here, so I've got the limit as x approaches 0 of sine of 3x plus 2 over cosine of x plus pi. So the thing I always like to do just to start out is just to see what happens if I were to actually plug that in. So let's see, I have sine of, this will be just sine of 0 plus 2, right, because 3 times 0 is just 0. And then this will be cosine of just pi, because 0 plus pi is just pi. So this will give me 0 plus 2, and then in the denominator I will have negative 1. So ultimately this will just equal negative 2, and that's it. So this one ended up being continuous, no special tricks that we need with anything like this. This is just a basic trig limit. So feel free to check out more examples like that if you need to. So moving on to 5 here. So I've got the limit as x approaches 0 of the tangent of x plus x over 4x. So in this case, if I plug in 0, I'm going to have 0 plus 0 over 0, so that's a problem. So what that tells me then is I've got to get a little bit more creative with this. Now there are a few different ways that I can go with this, but this is technically a fraction and it looks like I can break it up. So, why don't we just start there? We'll break this into 2 separate pieces. So I'll have the tangent of x over 4x, and then I'll also have, let's see, the limit as x approaches 0 of x over 4x. So you can see that this will simplify to 1 over 4. So this will simplify to just 1 over 4. And so that'll be the value of this particular limit. So this part is not so difficult. It is this, though, that we have a problem with. So this is giving me 0 over 0. So now we have to kind of think about our bag of limit tricks here, if you will. And I can't simplify this any farther. So instead, I really want to think about what it means just to be tangent. And usually one of the standard tricks would be to rewrite this as sine of x over cosine of x, and then I've got that really times 1 over 4x, and I'll just add that 1/4 at the end here. Okay, so now looking at this, I can see what I'm going to have to use here. So there's a particular theorem that I have pop up a lot, at least in my class. I don't know that all calculus classes necessarily learn this, but this is one that's pretty standard in my class. So it's this. So I've got sine of x, and I've got this x here. So I really want to put these two pieces together because then I can invoke this theorem. So let me rearrange things and let me clear off the theorem. So I'm going to have the limit as x approaches 0 of sine of x over x, and then 1 times 4 cosine of x. Now these pieces, we're going to be good to go. So sine of x over x, that's just me using the theorem I just told you about. So this is going to be going to 1. Now this is going to end up going to 1 over 4 times 1. And oops, I forgot about that 1/4 here at the end. So what all of this comes out to, I've got 1 times 1/4 plus 1/4. So just to be nice and clear, we've got 1/4 plus 1/4. So this will ultimately equal 1/2. And by the way, just before I move on, if you're looking to practice more with that, you just want to look for limits that use this particular theorem. Okay, so moving on to 6 here. So I've got the limit as x approaches 3 on the left of 1 over x minus 3 squared. So for this one, notice that when you plug 3 in, you get 0 in the denominator. You can't simplify this anymore, so this is probably going to either approach infinity or negative infinity. So we want to use a table just to kind of analyze this. So I've created a table and I've chosen 3 values that are getting closer and closer to 3 on the left side of 3. So if I plug those in, these are the y values that I get. So I can see just by looking at this that these are getting closer and closer to infinity, or they're getting larger and larger. Now also there are other ways that you can analyze this. I always like kind of just double checking with a table. But you can also tell that, you know that this is going to be a value a little bit less than 3 as you're kind of analyzing this. So this ends up being something negative, but when you square something negative, that becomes positive. So that's just another way that you can kind of analyze that. But a lot of times on tests, you kind of just want to back up your reasoning. So a test is on a test, if I could speak. Using a table is a great way to show kind of what you're doing or your reasoning on a test. So anyways, this equals infinity. So if you're looking for more problems like that, look up problems on infinite limits. Okay, so for this problem, I've got the limit as x approaches infinity of sine of x over 7x. And I just want to point out a really common error that I see with this one. It's very, very common that when students see this type of problem, they want to use this theorem. But this theorem only works when theta approaches 0. And in this case, we're approaching infinity. So we actually have to use a different approach here. So in this case, what we'd want to use is the sandwich or squeeze theorem. And this works really well when you have trig functions in particular, because you know for sine that it cannot exceed -1 or 1 in either direction, right? So that's great. And then if I want to now relate this to, oops, and I forgot the x, sorry, my bad. So if I want to now relate this to this function, so I can just divide all sides by 7x. And so now what happens to this limit as this approaches infinity? Well, this goes to 0 and this will also go to 0. Therefore, the middle one will go to 0. And so that's it. Now, if you're looking for more problems that have to do with this, I would recommend trying to look up limits at infinity with trig functions. Okay, so moving on to 8 here. So we've got the limit as x approaches 3 of 5 plus x to the 4/3. So this one is actually just a continuous function, so it's a nice one. We just get to plug it in. So this is going to be just 5 plus 3 to the 4/3. So hopefully you remember how rational exponents work. If you don't worry, I have a review video on that. So this is going to be 8 to the 4/3. Now, the way that you do this, first you take the cube root. So the cube root of 8 is 2, and then 2 to the 4th is equal to 16. And so this would fall under more of your just basic limits. However, even though they're called basic, it's very common that people forget how things like rational exponents work, so it might not feel basic. So again, if you feel like you forgot some of that, maybe go back and just review that. Okay, so for 9 here, so notice I've got the limit as x approaches 3 of 1 over x minus 1/3 over x minus 3. So in this case, if I plug in 3, I get 0 over 0 once again. So now I have to think through my bag of tricks. And so I have a fraction on top here, and so what I want to do is just try to get rid of the fraction. My preferred method of doing that is to multiply both the top and bottom of this whole fraction, because really this whole thing is a fraction too, right? I like to multiply the whole thing by the LCD of the two fractions. So I'm going to multiply this whole top part by 3x, and then I'm going to multiply also the denominator by 3x. And so just think about then what happens as I distribute the 3x to both parts of those fractions. What does that leave me with? Well, 1x times 3x is going to have the x's drop out. So on top I'm just going to be left with 3. And then 1/3 times the 3x, the 3's are going to drop out, so I'm just left with x. So now I've got 3 minus x over 3x times x minus 3. Now, notice that these are not the same. 3 minus x and x minus 3, they're not the same. But there is a trick that you can do to make them the same. So what you can do is you can factor out a -1 to flip the order of one of these. So I'm going to factor out -1 from this part right here, just the denominator. So I'm going to have the limit as x approaches 3. So this was 3 minus x on top. I'm going to put the negative in front of the 3x, and now look, I flip the direction of, or the order that was in the parenthesis, which then allows me to cancel those two things out. So now I am left with the limit as x approaches 3 of 1 over -3x, and now I get to just plug in that 3, so this becomes -3, nope, this becomes -1 over 3 times 3, so this is -1 over 9. Okay, so for 10 here, this is another limit as x approaches infinity, and this is just your standard rational expression. And really the key for this is to notice where the dominating term is. So the dominating term here is x to the 4th, and that is in the denominator. So this x to the 4th being in the denominator, it's going to drown everything out. So this whole thing is just going to end up equaling 0. Now, if you want to just be a little bit more detailed with that, you could also just divide everything by x to the 4th. So I can set that up real quick. Okay, so what I've done is I have gone through and I divided each one of these terms in this expression. I divided all of them by x to the 4th, and I just went ahead and simplified them. And the thing is once you have those x's in the denominator, all of those are going to end up going to 0. So you're really just left with this 0 over 1, which just comes out to 0. So that's how you can kind of show that if you need to show more detail. For 11 here, so I've got the limit as x approaches pi over 2 of inverse tangent of sine of pi over 2 plus cosine of x. So this one looks kind of crazy, but when that happens, just try seeing what happens if you plug in the pi over 2. So all of these functions are continuous, and when you have a composition of continuous functions, a lot of times you can just start evaluating and knocking them out. So for instance, The cosine of pi over 2, so I just plugged in that limit, that's just 0, right? So this is going to leave me with inverse tangent of sine of pi over 2 plus 0. So then I just have to take the sine of pi over 2, which is just equal to 1. So now I've got inverse tangent of just 1. And you could use a unit circle, but the answer to this is just going to equal pi over 4. And if you're looking for more practice problems, you can just look up limits of compositions of continuous functions. Okay, so for number 12 here, I have the limit as x approaches 0, and I've got 2 over the square root of 2x plus 4 plus 1. So I usually like to first just plug in everything and see what I get, and then kind of decide what to do from there. So let's just try plugging this in. So let's see, this is going to give me what? 0 plus 4 and then plus 1. So this becomes 2 over the square root of 4 plus 1. So this is just 2 over 2 plus 1. So this is just 2 over 3. And so that's actually it. We don't have to do anything with this. So this is just a basic limit. So if you're looking to practice more like that, you can just look up problems like that. So just be careful. Sometimes I think people go into what I call computer mode. They see the square root and they're like, oh, I got to multiply by the conjugate. Not always. Make sure you just think about it before you start. Okay, so with 13 here, I've got the limit as x approaches 2. I've got the square root of x plus 2 minus 2 over x minus 2. So if I just take a moment to see what happens with this one, so if I plug in 2, I'm going to have the square root of 4 minus 2 over 2 minus 2, and that's going to give me 0 over 2. So I can see now that I'm going to have to finesse this one a little more. So let me clear some space. So the standard trick you usually use when you see a square root is to try using the conjugate. So I will use the conjugate. And just kind of a piece of advice here, when you're multiplying, I don't recommend that you multiply out the bottom. Just leave these as factors, but multiply out the top. So let me go ahead and do that. And maybe you noticed that I made a little mistake, so I just corrected it. So I wrote the wrong expression into the radical, but I've fixed it now. Okay, so I went ahead and I multiplied all of this together. And so I'll just go ahead and simplify. And so now that I've simplified, I actually see the benefit of not multiplying out the bottom. So with this, actually, these two factors here canceled out. So now I've got the limit as x approaches 2 of 1 over the square root of x plus 2 plus 2. So if I plug 2 into this is going to give me 1 over the square root of 4 plus 2. So ultimately, I just get 1 over 4, and I'm good to go. So if you're looking to practice more problems that are like that, you can look up algebraic tricks for limits. All right, so for 14 here, I have the limit as x approaches 0, and then I've got this whole composition of functions. So where I want to start with this is just seeing what happens if I plug in 0. So let's see. Oops, let me switch my pen color here. So if I plug this in, so I get 4 times 0 plus sine of cosine of pi over 2 plus 0. So then I just have to take the cosine of pi over 2. And so that just comes out to 0. So then I just have to take the sine of 0, which is 0. So ultimately I get 0 plus 0. So this whole thing just equals 0. So for 15, I have the limit as x approaches negative infinity of 2 times the cube root of x plus 2 times the square root of x, all of that over 4x squared plus 5. Okay, so for this one, what I really need to do is identify where my largest exponent is. And this is really a shortcut for this. My largest exponent is right here in this x squared. Oops, let me, there we go. So you know then really just by looking at this that this whole thing is going to end up equaling 0. And if you want to show more work to prove that, then you can just divide everything by that highest power. But this is kind of like, in some ways, I think like if you just say that, you know, this is where the highest power is, and like that's probably enough. But if that's not enough, let me just show you the work for the other step you could do. Okay, so what I've done is I have divided everything in this expression by the term of highest degree, x squared, and I just simplified all the exponents, so this is what I would be left with. And so now by looking at this, so all of these pieces here, these all go to 0, and so then you're just left with really 0 over 4, which equals 0, which was the answer that we had. And this is really just a limit at infinity with rational expressions, so if you're looking to practice more with that, that's what you can look up. Okay, so for 16 here, so I have the limit as x approaches 0 of the tangent of x. So hopefully you just know this off the top of your head. So this just equals, this just equals 0. My pen wasn't working. Of course, if you weren't totally sure, you could always break this into sine over cosine. Sine of 0 is just 0. Cosine of 0 is 1. So I have 0 over 1, which still equals 0. If you're looking for more practice like that, that's just kind of one of your basic trig limits. So that's what you can look up. And again, you can look in the description, and I've got lots of other examples you can reference. Okay, so for 17 here, I have the limit as x approaches infinity of x minus 2 over the square root of x squared plus 25. So the thing here is that we have a limit at infinity. And really, this is like a rational expression. It's just got that square root in there. So when you think about the term of highest degree, I've talked about this in other videos. So if this doesn't make sense, I highly recommend you check out one of those other videos where I break this down a little bit more. But just to jog your memory of kind of what happens here. So you see this x squared here, but that is kind of playing with the square root. And if you think of how those two things interact with each other, the square root of something being squared is just going to give us x, right? So even though this looks like this might be the term of highest degree, really what this boils down to is just acting like x. So if I wanted to, then I could go ahead and just divide everything by x. So I'll divide everything here by x. And then I'm going to divide everything here by the square root of x squared, which really just equals x, right? But this is the only way that I can divide into this square root. So let me just show you how this would set up. Okay, so I've set this up, and now you can see, so I divided this whole square root by the square root of x squared. So once you have a square root and a square root, then you're allowed to divide those things in together. So then I was able to divide each term by x squared. So just kind of appreciate the detail that goes into that. So I'll simplify this one more step. And so now I'm ready to go with evaluating this. So we know that these 2 over x's, this is going to go to 0, 25 over x squared, this will go to 0. So really then I'm just left with 1 over the square root of 1. So ultimately this just equals 1. And so this just is a limit at infinity with rational expressions. So that's what you can look up. So for number 18, we have the limit as x approaches 2 on the right of x over x plus 3, and then 2x minus 1 over x squared plus 3x. Now, the thing that you would want to kind of watch out for here is whether or not this number would give you a 0 in the denominator, which it will not. So even though this is a one-sided limit, we don't really have to worry about kind of plugging it in, I guess. So don't let the one-sidedness always throw you off. So let's see, if I just go ahead and I plug this in. So let's see, I'm evaluating the limits. If I could write, okay, so I've plugged in my 2, so let's work this out. So this is going to give me 2 over 5. Let's see, this will be 4 minus 1, so that's 3. And then, so this will be 4 plus 6, which is 10. So then I get 6 over 50, which I can divide the top and bottom by 2 to get 3 over 25, and that's it. I'm done. So oops, as I go ahead and mess everything up. So if you're looking to practice more limits that look like this, you can look up kind of just your basic or one-sided limits. This one was nice, so we could just kind of plug everything in. So for 19 here, the limit as x approaches negative infinity of 3x plus the square root of 2x squared minus x plus 1. Now, this one is a little tricky. I've brought this up many times. When you're taking a test or when you're showing something to your instructor, you don't want to do calculations necessarily with infinity. A lot of instructors don't like that. But in the back of your head, you probably are doing calculations with this. And so if I were to just kind of think about what's happening with this, if I were to try to plug infinity in. So remember, infinity is going to kind of dominate everything. So what happens, let me back up here. So if I were to pretend to like plug this in for a moment, and this is considered kind of like a bad thing to do in math. So again, like this is something you do kind of on the side just to kind of think through the signs, but you don't write this down necessarily. Again, it kind of depends on the instructor, but I don't want my students to write this kind of stuff down. I know a lot of other instructors feel that way as well. So if I just kind of think through though, what is actually happening with the negativeness of this infinity? Well, this ends up becoming something negative, right? And then here, this is like 2 times infinity. And I only plugged infinity into this first part because this x squared is kind of drowning out the rest of this. The rest of this is just kind of noise. So hopefully that makes sense. So, oh, and this should be, I guess, squared, not that it really matters. But so what's happening here then is we've got this strange relationship of something negative with something positive. And so I guess it's kind of hard to tell just by looking at it as to what's happening. Because also if you were to take the square root of this, it kind of seems like we'd have like just negative infinity plus infinity. So we need to figure this out. And the way that we do this with an infinite limit is you're going to multiply by the conjugate. So let me clear some space. And I really didn't give myself enough space in this problem, so let me restate it, and I'll also show just multiplying by the conjugate. Okay, so now I've got everything written out here, so let's multiply everything together, so I'll work that out next. So now we have to kind of investigate what are we really left with. And this one is a little bit tricky because we still have quite a few exponents left in this problem. So my question is, where is our dominating exponent? So the dominating exponent is actually right here with the x squared. So you might think, oh, what about this x squared? Well, remember, you're taking the square root of this x squared. So the square root's kind of canceling out this square. Hopefully that makes sense. So this is where the dominating term is. So what I really want to figure out then is, how does that play out with this negative infinity? So the trick that you use here then is you divide by the next lowest term to kind of isolate what's happening with the dominating term. So let me clear some space. And now I'm going to divide everything by x. And I have to be careful when I divide into this square root, so I'll show you all the steps here. Okay, so stay with me here for a second because I think this is probably the trickiest part to understand about this. I'm going to do something that doesn't necessarily impact this problem, but it is something I want to show you. So first of all, look at this. I divided this by the square root. I divided this square root by the square root of x squared. I divided everything else by x, but I divided this by the square root of x squared. Okay. There's a little bit of a nuance here that, like I said, it doesn't super matter for this problem, but it can matter from time to time, so I want to make sure that I talk through it with you. So we know that x and technically the square root of x squared, these two things are like equivalent, right? So if I back up for a second before I really got to this, so what I wanted to do was I wanted to divide this all by x, and I know I can't do that because I've got this square root, so I wouldn't be allowed to do the division. Now, the thing about this that we have to take into account, and this is why this is tricky, x is going to negative infinity, so technically this would be going to negative infinity, so think about this. This negative and this negative, they would actually turn this into what? This would become a positive. So this right here, my negative, should actually turn into a positive. So I'm going to reflect that into the problem. And then I can make my adjustment right here that I need to divide this by the square root of x squared. And so now I can kind of finish this. So the funky thing that happened was that this flipped because I needed to account for the fact that this is going to negative infinity and just the way that this is going to work out. If I didn't make that change, we wouldn't really be able to tell that, like, I'd made that adjustment. So it's kind of a tricky thing. Feel free to leave me a comment if you have questions on this. This is kind of it comes up from time to time. In this particular problem, it doesn't really matter,
but I did want to just kind of walk you through that. Okay, so now let's clear some space. And now we can finish the calculation. So the whole point of this was to really just figure out what is happening as x goes to infinity. And since we knew that the dominating term was on top, that's why we divided by the next smallest term in the denominator, I guess. And so really now we just need to figure out all these other pieces are either going to 0 or to their number. The only thing that really matters here now is what's going to happen to this 7x as x approaches negative infinity. So as x approaches negative infinity, this will end up staying negative. So finally, we have an answer here. This will equal negative infinity. So that was definitely a tricky one. So if you're feeling super off your game now and you want to practice a couple more like that, I do have another video where I go through a bunch of these different types of limits. So that is in the description, so you can check that out and practice that as many more times as you want. Number 20, we have the limit as x approaches negative 3 on the left, and then we've got x plus 4 times the absolute value of x plus 3 over x plus 3. So if you've watched any of my limit videos, so this is kind of like at least one of my favorite one-sided limit type problems, because it really gets at if you understand the different sides of the function. So just a reminder, I'm kind of just going through the answers here. So if this feels like you need more explanation, I have lots of other videos where I break down why this works the way that it does. So just keep that in mind if you watch this and then you're like, oh no, that didn't totally make sense. So, okay. In this case, so we can see that negative 3 is going to give us a 0. And so at negative 3, that's actually kind of the point of the absolute value. And so this is that we are on the negative side of the absolute value. So the whole point of these is I want to rewrite this without the absolute value, taking into account which side of the absolute value that I'm on. So if I'm on the left side, I'm on the more negative side, which allows me to then rewrite, let's see, this as negative x plus 4 times x plus 3 over x plus 3. And so that will allow me to cancel out those x plus 3's. So then I've got the limit as x approaches negative 3 on the left of negative x plus 4. And now it's just as easy as plugging in negative 3. So this becomes negative 3 plus 4. So ultimately this equals negative 1, and we're good to go. So I don't know that all classes maybe go through this. I really like these types of problems personally. So you can look up one-sided limits with absolute value. Also, if you have no idea what the graph of these types of functions look like, I highly recommend that you go to like Desmos.com and check that out, because it's kind of a wacky graph and it really makes sense then why you have to take account in for each side of that absolute value. All right, so 21, we've got the limit as x approaches 2 on the right of 1 over the square root of x times x minus 2. So for this one, let's just see what happens if I plug in 2. Well, if I plug in 2, this will give me 2 minus 2, so I end up getting a 0 in the denominator. So that's a problem. The next thing that I think about is, can I simplify this? I cannot. And so what that means is this will probably equal infinity or negative infinity, because it's a one-sided limit. Okay, so the way that you can account for this then is you can make a table. You could also, just try to take into account what happens if you're on the right side of 2. But just to be thorough, I'll make a table. So there are 3 values that are on the right of 2 that get progressively closer to 2. So I just went ahead and calculated these y values on my own, and so this is what I got. And so you'll notice that the closer I get to 2, the larger the value gets. And I realize that these values are getting larger at a very slow rate, but they are getting larger. So you know that the closer you get to 2, this is just going to keep getting bigger and bigger. So that indicates to me then this is going to end up going to positive infinity. And if you're looking to practice more limits that are like that, look up infinite limits. I've got plenty of videos on them. You can check them out in the description below. Okay, and so for this final one, I've got the limit as x approaches 0 of sine of 5x over x plus x cubed minus 25x over x squared plus 5x minus cosine of pi plus x. So this one, I just wanted to put something together where you had to use a bunch of different limit techniques at once. So I think that this would actually be best to break this up into 3 separate limits. So let's see, let's make this one the green one, the yellow one, and the pink one, because I'm going to run out of space otherwise. So I'm allowed to evaluate each one of these limits separately. So let's start with this green part. So I've got the limit of, as x approaches 0, of sine of 5x over x. So just by looking at this, so I can't simplify it any farther. I know I'm going to get 0 over 0. So this is one of those limits that uses this theorem that this will equal 1. And so the problem is that this says 5x instead of x, so I need this to say 5x as well. So to finish this then, what I want to do is I want to multiply the top and bottom here by 5. So let me make a little space. Actually, I'll write it on the next line. Okay, so I've got the limit as x approaches 0, so we'll break that 5 out separately, and then I've got sine of 5x over 5x. So this goes to 1. So in the end, I have 5 times 1, so this just equals 5. So that is the value of the green limit. So let me just make some space. And I will just note that right below it. So I'll just write I'll write it in green. Okay, so moving on to the gold or yellow limit. So now I want to evaluate the limit as x approaches 0 of x cubed minus 25x over x squared plus 5x. So you'll notice right away you get 0 over 0 with this, and also you can factor an x out of the top and bottom. So let's start by doing that, and so this is with x squared minus 25 on top, and in bottom I've got x times x plus 5. And then you'll notice that you can also factor the x squared minus 25. So if I go one step farther, I have x times x minus 5 times x plus 5, and then x times x plus 5. So those x plus 5's drop out, and the x's drop out. So I'm actually just left with then the limit as x approaches 0 of x minus 5, and so that will just equal negative 5. Okay, so I'm going to write negative 5 right here so I don't forget, and let me clear some space. And so now working on the last part of this, so the pink part. So with the limit as x approaches 0 of negative, so notice I brought the negative with negative cosine of pi plus x. So for this one, I think I can just plug in the 0. So this becomes negative cosine of just really pi, right? That's it. And the cosine of pi is negative 1, so this just ultimately equals 1. Okay, so then I've got all my pieces of my limit, right? So at the end of the day, this entire limit, this equals 5 minus 5 plus 1. So we did all that work just to get 1. And so this one really combines several different ideas. In this one, I used both this theorem here, algebraic tricks for limits, just your standard trig limits, so kind of a little bit of everything in this one. Whew. All right. Well, I don't know about you guys, but I'm pretty tired. So, okay, I am super curious to know what you guys think about this video, or if you have suggestions for other things I could add on to it. Always listening to you guys. Thanks so much for watching, and I will catch you guys next time.